Today's daily question, obviously, what is energy? You guys basically all gave me an answer that was either yes or something to do with work. So if we look up the definition of energy, energy is the ability to do work. The ability to do work. All right. Anybody have a question pop up after they see that definition? Yeah. What's work? So there are two ways we can define work. The first way we can define work is the use of energy. So that is not helpful at all. While it's an accurate statement, circular definitions are not going to benefit us. So we're going to add in another definition here. Work is the capacity to change the amount, I don't want to use the word energy here. The capacity to change something's position or velocity. Something's position or velocity through the application of a force. So really, if we want to identify what energy is without having compound definitions, energy is the ability to use a capacity to change something's position or velocity through an application of force. Okay, kind of complex in there, but we're getting two new vocab terms simultaneously. Not exactly convenient. When we talk about energy, we typically categorize energy into two large groups: mechanical energy and non-mechanical energy. Mechanical energy is any energy that has to do with something's position or velocity. Energy based on position or velocity. Meanwhile, non-mechanical energy is everything else. So we could be talking about things like chemical potential energy. I'm just going to abbreviate PE for potential energy. We could be talking about electrical potential energy. We could be talking about radiative energy. We could talk about thermal energy, which arguably could be mechanical depending on how microscopic we're talking about things. Let's see here. Those are the top four that I can think of. Nuclear energy. All right, so our main focus this chapter is going to be on mechanical energy. You covered chemical in chemistry. We'll talk about electrical in March. We'll talk about radiative in April. Thermal, you kind of got a hint of that in chemistry as well. Nuclear energy, did you guys do any nuclear chemistry in chemistry? Like radioactive decay, that kind of stuff? Okay, so you got a hint of nuclear energy there then. We won't talk about it in physics because it's beyond the scope of our class. So when we talk about mechanical energy, we break mechanical energy down into two groups. The first group are kinetic energies. Simply stated, kinetic energy is the energy of motion. The energy of motion. And is calculated as kinetic energy is equal to 1/2 mass of the object times its velocity squared. Meaning that we could have units of kilogram meters squared per second squared. Rather than stating kilogram meters squared per second squared, because it's a bit of a mouthful, we developed a different unit to talk about energy, and that would be the joule, which is abbreviated J. And yes, it's named for a scientist whose last name was Joule. Okay, so joule is just the compound unit that we use to talk about kilogram meters squared per second squared. Doesn't matter what kind of energy we're talking about. All energies can be measured in joules, though you may be used to a couple of other types of energy. You may be used to, so other units include the calorie, or the erg. Erg, still probably the best unit ever made. Why did I say calorie twice? Capital and lowercase. What's the difference? He's right. A capital calorie, this is a food calorie. Food calorie. And is equivalent to 1,000 of these calories. So equals 1/1000th of a capital C calorie. And in terms of how big are these compared to a joule, well, it takes 4,186 joules to make a kilocalorie, if I remember correctly. Don't worry, you won't need to make that conversion. And an erg is the centimeters, grams, and seconds version. An erg is equal to 1 gram centimeter squared per second squared. And is used, for some reason, we use small units of energy in astronomy. I'm yet to figure out why when we're talking about incredibly large things, we use incredibly small units. No idea. But for our purpose, the joule is the main one we're going to talk about. All right, so looking at the equation for kinetic energy, there are two connections we want to make. The first connection is to the kinetic theory of matter. Anybody remember what the kinetic theory of matter was? We're throwing back here to either chemistry or 9th grade. Kinetic theory of matter. Remember what that was? Let's try an easier question. How many people remember hearing the kinetic theory of matter? Okay, so we got a few that are like, yeah, that might have been a thing. Okay, so the kinetic theory of matter had a few different parts. First part about the kinetic theory of matter was that it stated all matter is made up of atoms. Okay, that's pretty simple. The next one was that all atoms are in constant motion. Okay, and the last part of it was that for atoms at different temperatures, the higher temperatures move faster. And if an atom had, or a molecule, had more mass, it moved slower than an atom of, or a molecule of less mass at the same temperature. Well, that should make sense to us because really, temperature is a measure of an object's kinetic energy. Temperature is a measure of an object's particles' average kinetic energy. And as I increase the size of those particles, what must happen to their velocity to keep the same kinetic energy? Say again? Decrease, yeah. So as mass goes up, velocity has to come down in order to keep the same kinetic energy. Okay? So that's the first connection we wanted to make. Second connection we want to make, vehicle fuel efficiency. When you're driving, when do you get the most efficient gas mileage? Say again? Driving the speed limit? Other answers? When your foot's not on the pedal and you're coasting, okay? When you're driving slower, okay? So slower speeds get you better gas mileage. The reason slower speeds get you better gas mileage is because of this equation. So if we're working with some car and it has a kinetic energy of equal to 1/2 mv squared, if I have velocity 1 is equal to some small number, let's say 30 miles an hour, and I have velocity 2 is equal to 60 miles an hour, the amount of energy required to get to 30 is going to be significantly different than that to get to 60. 1/2 mass of your car times 30 squared versus 1/2 the mass of your car times 60 squared. You're using significantly more energy because you're squaring that velocity function rather than just being a linear function. If it were linear, it really wouldn't matter. You'd get about the same gas mileage regardless of how fast you were going. But because energy, kinetic energy, velocity is squared, we need exponentially more energy to go at higher speeds. So exponentially more energy is needed to travel at higher speeds. I had a student once who was convinced that I was wrong on this and told me, no, you get better gas mileage when you go faster. That's why you get better gas mileage on the highway than you do in town. What's wrong with his statement? It's wrong. You're right. Okay, why is it wrong? Why do you get better gas mileage on the highway than in town? He's right about that. Yeah, you're not stopping consistently. He wasn't accounting for the fact that when you're in town, you start and stop repeatedly. And just traveling at a constant speed, you would get better gas mileage in town. If you hit all green lights and never have to stop between point A and point B, you get better gas mileage. But it's because we're starting and stopping and that acceleration that uses up more gas. All right. So there's kinetic energy. The next type of energy we're talking about is potential. Yeah, even after other students in the class explained that to him, he still didn't believe it. It was rather impressive. Potential energy. Regardless of what kind of potential energy we're going to be talking about, potential energy is energy due to something's position. Energy due to position. Now, the first one we're going to talk about, the one you probably covered in physical science, is gravitational potential energy. Gravitational potential energy. All right? Gravitational potential energy is the energy that something has due to its capacity to fall. Energy something has due to its capacity to fall. And calculationally speaking, we can find that gravitational potential energy is equal to the mass of an object times the acceleration due to gravity times height. Talking in terms of units, what unit would I use for mass? Kilogram. What unit would I use for gravity? Meters per second squared. And for height? Meters. Much for difference? No, I just have to combine like terms here. So obviously gravitational potential energy is also in joules. Just a hint, all energy is in joules. Okay, so if we wanted to determine how much gravitational potential energy something had, we could talk about, say, we're going to put Gavin on top of a cliff. And that cliff is 100 meters tall. Okay. Gavin probably has a mass of, I'm going to go 80 kilograms. It's going to be roughly 185 Am I low? $87 kilograms, so more like 194. Really? Wow. Okay. Wouldn't have guessed that. Way more muscle in there than I thought. I've only got 20 pounds on you? Holy cow. All right, so if we wanted to calculate his gravitational potential energy standing at the top of the cliff, we could calculate that as 80 for the purpose of this problem, times, well, acceleration due to gravity, 9.8, times the height of the cliff, 100. So 80 times 9.8 times 100, and we get his total energy sitting at the top of the cliff to be 80 times 9.8 times 100, 78,400 joules. Okay. Likewise, we could put, let's say, Abu at the top of the cliff. I'm going to go 70 kilograms for roughly 150. All right, I feel better about my guessing ability here. So 70 kilograms times 9.8 times 100, giving us 70 times 9.8 times 100, 68,600 joules. All right, so sitting at the top of the cliff, Gavin clearly has more energy, yes? Okay, next question. They both jump off the cliff. Who hits the ground first? Say again? Same time, why? Gravity doesn't affect one more than the other. Acceleration is still the same. These aren't changing. Even though he's got more energy, they still hit the ground same time. All right, so kinetic energy, gravitational potential energy, different types of energy, using them singly, like here, just talking about how much energy each of them have, really isn't useful. The only reason that we would ever talk about energy is because of the law of conservation of energy. Law of conservation of energy. All right, so you guys remember law of conservation of mass from chemistry. What was it? Mass can't be created or destroyed. It's why when we balanced chemical equations, we had to have the same number of each element on both sides. Otherwise, we destroyed or created mass, and that's not reasonable. So law of conservation of energy follows the same pattern. Energy can't be created or destroyed, but it can change forms. Energy can't be created or destroyed, but it can change forms. Simon, did I cut you off there? Did you have another part you were adding to the end? Okay. All right. So mathematically what this means is that the sum of the energies at point A must always be equal to the sum of the energies at point B, regardless of what type of energies are present. East from the top, nothing is stopping that roller coaster. Nothing is, well, other than the brakes, but nothing's trying to propel it forward. There's no extra energy being added. So the highest hill is always the top, or sorry, the first hill is always the highest. First hill is always the highest. All right, so we've all been on roller coasters. So who likes to sit in the back? Who likes to sit in the front? Front. Who's more of either an I don't care or middle of this middle of the car? Okay. All right. So when you're getting into your roller coaster car, let's talk about one of those long chain ones where you like ride 16 people at a time. If you're looking around and seeing who else you're riding with, who are you hoping is in some of the other cars? Who do you hope is in the same roller coaster car with you to get the best ride out of your roller coaster? Okay, well, beyond it being entertaining that way. Say again?
A
Okay. Other ideas? Say again. Someone's not going to puke on you? Why? Okay, so if we have more mass in the roller coaster, we have more energy. And we just showed up here that more mass meant more energy. Okay, so let's take a look at this. Let's say for our roller coaster, we're going to go with a 40-meter high roller coaster. All right, and we're going to say that down here at the bottom, what kind of energy should the roller coaster have when it reaches this bottom of this first hill? What kind of energy? Kinetic. So this is going to be kinetic energy. And what type of energy is the roller coaster going to have at the top? What kind of potential? There we go. Gravitational potential energy. All right. So gravitational potential energy to kinetic energy. We can actually figure out how fast this roller coaster is going to be going when it reaches the bottom, simply based on the height. And let's figure out how much mass this roller coaster is. So somebody big, let's add in the roller coaster mass. Let's say the whole system is 1,000 kilograms of mass. Okay? 1,000 kilograms, and we're going to turn that into kinetic energy. So by the law of conservation of energy, that says the sum of the energies at point A, must be equal to the sum of the energies at point B. So that means that my gravitational potential energy at point A must be equal to my kinetic energy at point B. All right. When working conservation of energy and basically anything in this chapter, it's difficult because you always have to come up with your own equation in terms of what the sum of all the energies is. I can't give you a single equation and say, you should apply this in this situation. No, you've got to create your own every time. It's easy because what have you noticed you don't have to worry about so far that was a pain when talking forces or motion? Vectors. Energy is a scalar unit. We don't have to worry about direction in any of this. Coincidentally, that probably makes this the easiest chapter of the year. So it doesn't matter which way anything is going. All we care about is magnitude in each of these, or size. All right, so we've got mass, gravity, height equals half mv squared. So 1,000 times 9.8 times 40 equals half times 1,000 times v squared. All right, so I'm going to multiply these together. 1,000 times 40 times 9.8, 392,000 joules equals 500 v squared. Divide by 500, take the square root, and we find that this cart is going to be going 28 meters per second. All right, so Gavin put an offensive lineman for the Vikings in this car. And now we're going to change it up. Winter Olympics are coming up. And instead of a football player, we're going to throw in, somebody who rides the luge. Everybody knows what the luge is, right? Okay, so those are like really teeny people. And we're going to see how fast this would be going. Problem 2, now using a total mass of, let's just have that, 500 kilograms. So we're still accounting for the mass of the car, and the mass of the rider is included in that. Evidently, I put a really big guy in that first one. What do you predict? What do you think is going to happen? What's going to happen to the velocity comparatively? Not going to be as fast. Any ideas as to how much different? Half? Other thoughts? Okay. Take a minute, calculate the speed. So regardless of whether it's a whole bunch of really little itty-bitty people or a whole bunch of football players coming right off of the offensive line, they're going to have the exact same ride every time, regardless of where in the car they are, because the mass cancels out and all objects accelerate at the same rate due to gravity. So in terms of energy, sure, yeah, the heavier guy had more energy, but the heavier guy needed more energy to get going the same speed. So yeah, they had more energy, but they needed more energy. So they wind up with the exact same pace. All right, let's take a look at another spot. Let's say point C. And let's say point C, they are now 5 meters above the ground. Take what we just used, and either rider, because it obviously doesn't matter. I want to know how fast the roller coaster is going at point C. All right, let's take a look and see how this should be done. So I'm going to take 1,000 times 9.8 times 40, which we already found to be 392,000 joules. And I'm just going to work with the heavier rider because I've got a number for it. And we already know that it doesn't matter which one we're talking about. It's going to go the same speed. And on the other side of my equation, I'm going to show that there's both gravitational potential energy and kinetic energy. Okay? So for this problem, now I can go ahead and start filling in values. 1,000 times 9.8 times height c, which is 5, plus half times 1,000 times v squared. Okay, so 1,000 times 9.8 times 5, 4,900. I'm going to subtract that off from the other value, 392,123, minus that. And then I'm going to divide by 500. And lastly, I'm going to take the square root. And I'm going to get 27.8 meters per second. So not dramatically different compared to the very bottom here. Correct? Did you guys also get 27.8? Do we have different answers? So this one is still a potential energy, but this next one that I'm going to add in here is elastic potential energy. Elastic potential energy is the potential energy that exists on something due to the presence of a restoring force. The energy something has due to the presence of a restoring force. Okay, so when we're talking about these, this could be something like a slingshot, could be a rubber band that's stretched back, could be a spring that's stretched, it could be a car shock that's been compressed, it could be surgical tubing that's been stretched. Did any of you guys build some kind of a catapult or slingshot for your pumpkin launchers, or were you all trebuchets? You guys had a catapult. What did it use? Oh, that's a trebuchet. If it's got it. Oh, I see. You had the modified version. Okay. The trebupult. Okay. What'd you use? Okay. So we had some kind of slingshot. Did it use like bungees? Oh, right. But it twisted it in the bottom, right? Okay. It does say restoring force. And determine the total magnitude of elastic potential energy something has stored. Elastic potential energy is equal to 1/2 K, where K is a spring constant, times x squared, where x is the displacement from the rest position. From rest. So a spring constant is basically a statement of elasticity of a specific object. So if I take a rubber band here, this rubber band has a specific spring constant. The spring constant is basically how stretchy, not very, is the rubber band. So as I stretch the rubber band, I have more force acting back towards the center because I've got a greater X value, so if this is the rest position, I stretch the rubber band, X is increased, I now have elastic potential energy. The amount of elastic potential energy is entirely dependent on what kind of rubber band I stretched and what that specific rubber band's spring constant is. Okay? We'll leave it there for today because the bell's going to ring in 4 seconds.